branches. So means that one of the poles, let's say, starts moving from here, it goes here, and then it either goes to this one or that one. The other one moves from here to here, and we have symmetry with respect to real axis, so the other one goes from here to here, and so the poles of the closed loop system are gonna move like this or like this. One of them is gonna move like this, the other one is gonna move like this. Okay, and if both poles are on the left hand side, then the closed loop system is stable, otherwise the closed loop system is unstable. So we have to figure out what's the maximum value of K that we can have so that our system is stable. Okay, again, I'm gonna use this formula, right? Because at this point, at this point, 1 plus K GS HS has to be equal to 0. Okay. So let's just write this down. 1 plus K GS HS has to be equal to 0. We have GS HS. So means that 1 plus K times S minus 4 times S minus 3 divided by S plus 1, S plus 2 is equal to 0. Means that S, let's just like simplify this. S2 plus 3S plus 2, this is this term multiplied by 1, plus K times S2 minus 7S plus 12 is equal to 0. So that means that S2 times 1 plus K plus S times 3 minus 7K plus 2 plus 12K is equal to 0. I just factored out all the S squared terms here, S term here, and the constants here. Okay. So you can see that this is a second, or this is a quadratic equation, and it has two solutions, which are these two, right? But these are pure imaginary numbers. Pure imaginary numbers. Okay. If a quadratic equation has pure imaginary numbers, it should be in the form, for example, like this: S2 plus 1 equal to 0, right? It can't be in the form S2 plus S plus 1 equal to 0. This is not going to be pure imaginary. It has some real component, right? So for a quadratic equation to have pure imaginary answers, right, this term has to be equal to 0. So it means that 3 minus 7K is equal to 0, or K is equal to 3 over 7. So this happens at K equal to 3 over 7. The same thing here. So for our system, our closed loop system, to be stable, K has to be between 0 or smaller than 3 over 7. If you increase it further than that, your closed loop system becomes unstable. Look at the original GS times GHSH. This one is always stable, but the closed loop system, it's going to become unstable if k is bigger than 3/7. Okay, so that's how Ruth Lucas can help us find the basically the region of the stability of the closed loop system. One other example. I know this is like a little bit challenging if you guys especially haven't seen this before. In the exam, I'm not gonna be questioning like difficult Ruth Lucas questions, but it's gonna be similar to what you've seen before, exactly similar to what we've seen before, and I'm just gonna focus on the easier examples, not the challenging ones. So this, I think this is gonna be the third example we're gonna see. This one, it's 1 over s minus 1 times s plus 2. Okay, so again, the first thing we have to do on the s-plane, real, imaginary. Okay, we're gonna see where the poles and zeros of this term are. There are no zeros. There is one yeah, I'm sorry, this is s plus 1. Okay, there's one pole here, minus 1. There is another pole here. There are no zeros. Okay, there are actually no finite zeros. There are zeros at infinity. There are two zeros at infinity. As s goes to infinity, there are 2 zeros. Okay, but there are no finite zeros. Okay, again, we know that we are gonna have some we're gonna have a branch here, right? So at k equal to 0, we start from a pole. At k equal to 0, we're gonna start from another pole. So we have 2 poles, right? They just move towards each other, but they're gonna go in a different direction. We wanna know how this is gonna happen, right? So this is like where the last rule is used, right? So like this, like we don't have any zeros. We're gonna have some linear like linear lines, asymptotes, and we're gonna see like where exactly that basically branching happens and at what angle. Okay, so to do that, we're gonna use these 2 formulas. The first one, it says that the place of branch separation happens at summation of finite poles. So this is 1 and minus 1 and minus 2 summation. It's going to be minus 3 minus finite zeros. There is no 0, so there's no finite 0, so this is going to be 0, divided by finite poles, number of finite poles, which is 2. We have 2 finite poles, minus finite zeros. We don't have any finite zeros. So this is going to be negative 3/2